Hello and welcome to Sean White's Solar and Energy Storage Podcast. Today, we're in San Diego at InterSolar, and we have Charlie Hasselbrink of Caelux. And we already talked to one of your colleagues before too, and his name is?
Scott Grable, our CEO.
Scott Grable, the CEO, and we were talking about perovskites. And so if you really want to get into it, you'll listen to this podcast and then that one, and then you come back to this one, because that's how I learn, is I do things over and over and over again.
Okay.
Yeah. So Charlie also was just telling me that he worked for SunPower when they got bought up by Total, and he went to Paris and he got to see how they work with lots of cigarettes and things like that. It's probably a different
a lot more
company.
smoking on the smoke breaks than there in the US. Yeah, that's for sure.
Does that help with solar cells or something? A little bit of nicotine?
I don't think so. I think that's good for them, actually.
Yeah.
Pretty sure.
Helps them digest the sunlight better.
They're more relaxed solar cells.
And so you are a technical person. You're the CTO. And so let's talk a little bit about your technology, about what the perovskites do and how all that works.
Yeah, okay. Well, so perovskites are kind of a new technology. It's like equivalent of saying, if you ask yourself 100 years ago what was silicon, you might have the same questions, right? So perovskite simply is a material that you can start out as a liquid, as a solution. And if you dry it just right, it can form a crystal. And that crystal is a semiconductor, and that semiconductor can convert light into electricity.
So let's even focus on that a little bit. So it's a liquid. So the perovskites, is it called perovskite when it's a liquid?
No, it's called a precursor at that point.
It's called a precursor. Yep. Is it edible?
Nope, wouldn't want to eat it. Yeah, it's got lead.
Is that? I think I have a little bit right here.
Delicious.
I think it tastes good. It seems pretty healthy to me. And so this precursor, it's got a bunch of different chemicals in it, and then you set it out and it dries? Is that kind of what happens? Or?
Yeah, so you have to dry it just under the right conditions. You want to dry it pretty quickly and pretty suddenly. You want to go from a liquid precursor solution. But yeah, so people can use air knives and things like that, and they'll print a sheet of it nice and thin. And then they'll use an air knife to suddenly dry it, for example. People use different methods, or vacuum drying, different methods to do
air knives and vacuum drying. Can you bring an air knife on an airplane?
Yeah. Nope, can't do that. Just not for the least reason that they're too big. But
okay.
Too big to fit in heavy.
It's not like a knife, is it?
No, it's like when you walk in the grocery store and you suddenly have this air curtain that shoots down on you, that keeps the bugs from getting through.
Oh, okay, kind of like those hand washing things.
Right, kind of like that. Exactly, like the Dyson Airblade.
Okay. And so you get this liquid, and what's in the liquid?
So the liquid is typically a mixture of methylammonium or formamidinium iodide, a lead iodide, and other random, all sorts of other additives that people use in there. And so the combination of that basically has a formula of ABX3, which is A is either methylammonium or formamidinium, so hard to say that word. The B is lead, so you have one part of that, and then you have three iodides or bromines or chlorines, and some combination of those. And the idea is to get a crystal structure that forms just right, and then it's a really good semiconductor.
So how is it forming that crystal structure? I know for solar cells, when you're making silicon solar cells, I should say, that it's very difficult to make that crystal.
Yeah, that takes a lot of heat and a lot of time, a lot of energy to grow and then keep that crystal. They have to do all kinds of zone growth processes where they're basically trying to purify anything that's impure in there and make a single crystal, super hard. With this, you just take this liquid, you basically make a thin sheet of it by various possible means to do that. People use different methods. So imagine just printing it in a really small, thin layer that's maybe a few human hairs tall, and then suddenly dry it with one of these air knives or with a vacuum dryer. Just suddenly you apply a vacuum, and it'll suddenly turn dark. So it'll go from basically a yellow to greenish looking liquid, and it suddenly turns into a nice dark crystal that's going to absorb sunlight.
Okay, and the way that you're doing your technology, right? You're layering it on top of regular crystalline silicon?
So the way we do ours is that we print directly on glass, and so that glass has a conductor already on it, a transparent conductor, just like the kinds that are on your car windows. So in your car windows where you turn on your heater to defrost your windows, they're actually using a transparent conductor in there that actually, it's also a resistor. Okay. And so that same kind of conductor is used to conduct electricity on one side, and then we apply another conductor on the other side, and then we can harvest the holes in
Can we talk about what a transparent conductor is? Because that's also kind of weird too. So is that like a touch screen, like your phone or something?
Yeah, so you have conductors, the same kind of stuff as on the touch screens on these computer screens and things like that we're used to using every day. Your iPhone or any cell phone you've got pretty much has a transparent conducting layer on it.
Okay. And so what is that transparent conductor? That seems kind of weird, like a clear wire.
Yeah, it is. It's funny because the undergraduate physics version of it is like, oh, you can't do that. That's impossible. You can't have a conductor that doesn't become a hard boundary condition for waves or electromagnetic waves. But it turns out it's possible to do it. Now it's not as good a conductor as metal, for example. So it has some resistance to it, but it's conductive enough. So it's typically a metal oxide. So examples that you can get are indium tin oxide, fluorinated tin oxide.
So
like
is that what we're touching when we're touching our touch screens then? Is it like...
Yeah, there's basically, I don't know that much about how touchscreens are designed. And these days, I used to know a VP of research at ELO Touch Systems, but should have asked more questions at the time. But yeah, that's essentially how they're working. So they're using lots of little conductors there and detecting where your finger's located.
Wow. Okay. Wow. That's pretty weird. I remember one time I was sitting at the SNEC solar show in Shanghai, and there was some kind of presentation where somebody had... It was like a computer display that actually could absorb photons, and it was PV all at the same time. It was probably like super inefficient, but it was,
Right.
It was kind of strange.
Yeah, you'll let the visible through, but they'll still turn the infrared typically. The trick that's being played there is they'll absorb just the infrared and let the rest of the visible light come through. So to you see nothing, but it's still able to absorb the infrared and convert that to electricity. Yeah,
Wow.
several companies have done that. Ubiquitous, View. View is actually using the same idea with these transparent conductors, apply a voltage, and then suddenly could make them so they were reflective, and so they could actually keep buildings cooler. Ubiquitous was trying to turn energy from those infrared light that hit those windows, still make them optically clear, but then convert some of that infrared light into electricity. So
It kind of makes me wonder what the world's going to be like in 100 or 200 years.
yeah.
Or just like the window is going to be a display, it's going to absorb the photons, and all kinds of crazy stuff.
Well, I'm glad you mentioned that. One of the interesting futures that I can see, I'm not a futurist really, but one of the futures for solar here that's possible is that, so now you've got this trick that you can play where you say, I've got a clear conductor and I can put that on both sides of a piece of thin film absorber, and I can choose those absorbers to absorb only certain parts of the frequency spectrum of the electromagnetic spectrum, right? So if you do that, now imagine you say, well, let's see, what do I want to do with the ultraviolet part of the spectrum? What do I want to do with the visible part of the spectrum? And what do I want to do with the infrared part of the spectrum? So imagine you had 3 separate layers. Imagine they're printed on a sheet. It could be on a roll-to-roll sheet of this thin film that only absorbs the UV and converts it to electricity. Another layer only converts the visible, and another one only converts the infrared. You could take all 3 of those, and you could actually just laminate them together, put them onto a piece of glass, maybe put another piece of glass to protect them on the backside, and you've got yourself a really efficient solar panel.
That's like a solar sandwich.
And like a solar sandwich.
And you got visible on both sides of it.
So here's what's cool about that. So I think of photons as being, the people think of them as take a photon and I convert it to an electron inside of a semiconductor. But every photon has a different voltage. So they'll come in at different electron volts. And so an ultraviolet photon has more voltage than an infrared photon. Now, as it turns out, the reason we kind of originally started with silicon is because silicon would absorb the entire spectrum, but it would always convert it to the same voltage of 0.7 volts roughly. So every silicon cell that you buy or can see on this trade show floor today is going to be converting somewhere between 0.7 and 0.7.
It's like open circuit voltage or something.
Open VOC is going to be between 0.7 and 0.74, somewhere in there. Never much better than that. But here's the thing. If you said, well, I'm going to make an absorber that absorbs in the band gap range of, say, 1.5 volts or something, I might end up getting 1.3 volts out of that. So silicon absorbs at 1.1. It's got a band gap of 1.1. And what you get out of that is 0.7 volts out of that. If you absorb photons at 1.5 volts and you have a 1.5 band gap absorber, you might get something like 1.0 volts out of that. And if you go at 1.6, 1.7, you'll get about 1.2, which is what we do. We actually absorb at about 1.65 EV is our band gap. That corresponds to the light going up to about 750 nanometers. But we get a lot more voltage out of all that's part of the spectrum. We get almost 1.2 volts out of that, as opposed to silicon that only could get 0.7 volts out of that. It'll still basically convert the rest into heat. So all the rest is lost.
So in kind of with your technology, I think what you're doing is you make a piece of glass, you sell it to a module manufacturer, and then they have perovskite on the glass, and then they combine it with their silicon. And so how do you match the voltages of these 2 different technologies?
Yeah, so we can use lasers to scribe our cells. We basically have this very thin film that's applied to the surface, and we use lasers to scribe the cells and define how many cells we want. So we can decide, all right, we've got 1.2 volts per cell. I want to make a 60 volt panel. I need about 50 cells. So 50 cells, and our cells are long and skinny. They're about 5 millimeters wide and about 2 meters long. So take those 5 millimeter wide cells and put 50 of them. You got 250 millimeters. You got about a quarter of a meter.
So you get like big long stripes.
Yeah. So you get these big long stripes, and you get a group of them, and then you put a tab there. And then so you can have the voltage build up along the width of the panel, and then you can have the voltage fall down along the panel, down to the next conductor. So you can have plus, minus, plus, minus, plus, minus. So you can set up your panel that way and kind of align it with the silicon as well. If you make it so that the tabs line up and the spaces between the silicon cells, even better, because then you don't have any shading loss in there either.
So you kind of like match the ratio of cells.
That's right. We basically match the voltage. That's the key thing, is match the voltage.
Kind of reminds me of like the old days with solar, how you would match your ratio of solar cells to lead acid battery cells. And so it would be like 2 volts nominal for a lead acid battery cell, a third of a volt nominal for a solar cell, 6 solar cells to 1 lead acid battery cell.
Exactly
so
the same
36
idea.
Cell module, 12 volts.
Exactly the same idea. Just match that voltage. And here's the other big win there, is that the voltage of a solar cell doesn't change much as a function of how much sun there is. So the current changes an awful lot. So from morning to afternoon, the difference is enormous on how much current you're going to get out of your rooftop, for example.
Sure.
But the voltage is almost always about the same. You'll notice that if you look at your inverter, you'll see it's always about the same voltage.
Yeah, because when it gets brighter, it gets hotter, and if anything, the voltage might even go down a little bit.
Right. Yeah, the voltage goes down with a little hotter temperatures. That's right. Yeah.
So that's pretty cool. And then how about the temperature coefficients for these different technologies? Are they similar or a little bit different?
There's a little mismatch there for sure. So the silicon, for example, will have something like call it about 0.5% per degree C, something around there. Depends, about 0.7.
0.3 to 0.5.
Yeah, somewhere in there, 0.2 to 0.5.
I guess it depends if you're talking about open circuit or maximum power and all that.
Can vary and it can vary from panel to panel a little bit. But yeah, something around that. Ours is about 0.2. Here's the interesting thing. We've had chemistries that actually go negative, go to minus 0.2 in certain temperature ranges.
Better when it gets hot or something?
Which is a little surprising, which is counterintuitive to what you know about silicon cells. But yeah, so we've seen that before. Right now, the good news is that those coefficients are small, and we can also account for them when we design so that, hey, when it's up and it's kind of closer to its normal modular operating temperature, we're at a pretty good match still.
Okay. Cool.
And the other good news is that, hey, when you're matched on voltage, even if you're 10% off, plus or minus, it's still fine. You're actually really close to the max power point. So you're still fine, right? Because the PV curve looks like a parabola, and so you're at the top of the parabola. It looks like a skewed parabola.
Cool. That's pretty neat. And so this technology, the Perovskite that you're putting on the glass, that was a liquid that you then turned into a crystal, that technology is called thin film, correct?
Correct.
So you're mixing thin film with crystalline PV when you're doing that.
That's right. But we keep them completely isolated. And for us, that's an important strategic move, because what that means is that we can do our processing without having to think about mechanical, chemical, or really electrical coupling at all.
So why isn't everybody using your technology? Are they stupid?
So there are plenty of companies doing what's called 2-terminal tandems. And when you build a 2-terminal tandem, you just print right on the silicon. And when you print right on the silicon cell, you got a couple of challenges there. One is that you're printing on a textured surface, which can actually make the printing process easier, because now you have like kind of grips with the surface tension grips onto that cell. And the other good news about that is that you get slightly higher efficiencies. So you'll get 4 to 10% higher efficiencies with that. The bad news is you have to be matched on current. And there's some time of the day when you're definitely mismatched. So if the sky is bluer in the morning, redder in the afternoon, and we get back to bluer in the late evening, when it's blue, the perovskite's going to absorb more. When it's red, the silicon's going to absorb more, because the silicon absorbs better there. The spectrum shifts that way. So that's the problem. So you're going to be mismatched for sure. And the question is, okay, does the mismatch enough to cause reverse bias? There's certainly some time of the day when it will be true. Say all the silicon is going to be trying to push more current than the perovskite can push. When that happens, the problem is the perovskite says, I'm going to have to go into a mode where I'm generating heat instead of generating current.
And so reverse bias is when the silicon is pushing current backwards in the opposite direction through the perovskite?
It's pushing it through, but what's happening is that the voltage will, instead of it, so normally what happens is the current flows through the perovskite, the voltage goes up. In this case, when it's in reverse bias, the voltage is going to go down, and that's bad. So you don't want the voltage to go down in the direction of the current.
Yeah, and sometimes I tell people that a solar cell is an LED in reverse, and if you took a solar cell and you put voltage on it at night, it will put out light that's invisible because, I guess it would be like infrared light is what it's putting out.
Yeah, and that's true for a silicon cell, and that's specifically because its band gap is in the infrared. It's around 1100, and our band gap's at 750. So when we do the same thing with ours, you can see it. You can see it. It's red. Yeah, wow. You get a little red LED. Yeah,
that's right. That's cool. Maybe there would be some kind of application where somebody would even want to do that. Like it'd be like Christmas time or something like that.
Turn your solar panels into big red things on your...
I'm just thinking of 200 years in the future.
Well, in the sandwich thing we talked about earlier, where, hey, I could pick, I can pick a band gap that's in the green, I can pick one that's in the red, I can pick another one that's in the deep infrared, and you could slice up the spectrum like that to get as much efficiency as you want, as you can achieve out of it. But yeah, then that would give you the option of changing, multiple LEDs stacked on top of each other. Each one's transparent to the wavelengths underneath. The problem is you'd have to flip the solar panels over because the light wouldn't get through the layer above it, but it'll get through the layer. Actually, no, I take that back. No, it would get through because it's still transparent to those longer wavelengths. Yeah, no, that would work, yeah.
That's pretty cool. There's got to be some kind of application there. Kind of reminds me, did you ever see that video that was like solar freaking roadways? It was like 10 years ago or 15 years ago,
like
something
in Spain or something like that they tried. They did a demo of this or something.
It was here in the U.S. and it was just like these people. I remember it was like they're using in-phase inverters and they were like showing these and they're making streets out of solar, and they had all these videos of how you're going to like drive your cars on them, and they had LED lights in them, and you could change the lanes and all this kind of stuff. And people in the solar industry were just like, yeah, give me a break. We're going to drive trucks. We can't even keep our roads together as it is. And then the people that were not into solar and didn't really understand the details, they were just like, yeah, this is the neatest thing ever. This is the future. And I remember they had like a moose coming out, and it would step on it, and then it would like the whole roadway would change color to warn you that there's a moose on the road.
That's pretty cool. No, I don't remember seeing that, but I do remember seeing one where it was the solar roads, but I thought it was in Spain or something. And I remember thinking to myself, gee, the problem is you're going to have partial shading of some of those cells. And anyone who did reliability like I did for about 10 years at SunPower almost, now Maxion,
they probably
know
didn't
that
allow
reverse bias isn't great for solar cells, obviously. Reverse bias is bad. So you really, if you shade one solar cell and there's 1,000 others in series, all connected to the same inverter, the inverter will choose to run the current at a high current that will, unfortunately, now once you shade one of those cells, it can't produce that current. And so now that thing turns into a big heater. That's a problem.
Yeah, and that's why we have bypass diodes.
That's right. That's right.
Speaking of bypass diodes, how do they work with your technology?
Same way. We can set up little substrings within the panel, and we can apply the bypass diodes in the same way. Are you sharing
the same diodes, I guess?
Yeah, we would share the same diodes. And the other good news about this is that actually, because now you have two paths for the current to go through, so there's two really good things. The first one is that our reverse bias voltage is not as bad as silicon. Silicons can be like minus 10 volts, and then so that's why it dissipates so much power. You get, call it 6 amps through minus 10 volts. Guess what? You have 60 watts that you just lost. Versus us, I think our reverse bias voltages are much lower, just a volt or two. And then the second good thing is that if you have a section that's shaded, is that there's two different paths for the current to go through. The current can choose to go through the silicon, or it can choose to go through our material. And they're shaped, the cells are shaped so differently that only one of those is probably going to be fully shaded, right? Going to be hard shaded. So that will give that alternate path for current. And then the third thing is the silicon cells are the ones that really have the big reverse bias voltage that gives them all that power dissipation. But in this panel, we're absorbing 2/3 of the sunlight up front. Only 1/3 is going through to the silicon, roughly. It's about 40% is going through to the silicon. And the silicon, it's right about 40%. So now that doesn't get as hot because there's only 40% of the current. So it only heats up 40% as much.
Oh, cool. Yeah. All right. Awesome. Wow.
Yeah. So there's lots of benefits here with the tandem design, for sure.
Okay.
And there's 4-terminal arrangement where you do them in parallel. If you force them to be on top of each other, so we got sidetracked a little bit, but if you place perovskite on top of silicon and you force them to be current matched, which is what happens in what's called a 2-terminal tandem, all the current going to the silicon cell is common. It's all also then going straight through the perovskite cell. And in that case, if you have hard shading, guess what happens? You've gone into this reverse bias and you've got that problem. So you don't get these same advantages. You're still relying on those protection diodes. And then it gets worse because now let's say the perovskite is actually degrading at a different rate. Let's say that the current that can be produced by the perovskite is degrading at a different rate over 20 years from the silicon underneath it. Well, guess what? That mismatch just gets worse and worse and worse over time.
We interrupt you for a very important announcement. Shaun White's Solar and Energy Storage Podcast has been brought to you by Shaun White's Solar and Energy Storage Podcast. That's right, Shaun White is sponsoring his own podcast, and he wants to remind you to go check out some of his classes. You can go to SolarSean, that's Solar, SEAN.com, and then click on the links to check out his classes. You can check out his heat spring classes, and you can also hire him to teach classes for you, like at your company, something like that. Now back to the show.
Okay. And so that's the one where they put it right on the cell.
That's right.
Yeah. Not your technology. Yeah.
So, I mean, it can give you better efficiency, but it's got all these other penalties. Yeah.
Okay. Right.
And I really think that the future is going to go to, so right now in space, for example, they use triple junction cells. So it's really 3 cells stacked on top of each other. You can do that in space because guess what? The spectrum never changes. There's no sky.
Yeah.
And there's no scattering that's changing the spectrum of the sun.
Yeah, if you hate clouds, good place to be.
Yes, yeah, no clouds in space, so no problem. So fantastic for that arrangement. But actually the 4-terminal would then, if you want to do a triple, would be a 6-terminal arrangement. And again, just match the voltages, design the number of cells so that they match, and then time together at the ends where they come out of the panel.
Awesome. That's pretty cool.
So you could really get some pretty high efficiencies. I think that sets right now, triple junction cells are getting 47% in the lab.
It's crazy.
So imagine someday we would have 47% terrestrial modules. Can you imagine what that would be?
Is that like 200 years?
And I don't think so. I don't think so. I really think between various thin film technologies, we've got CAD-TEL, pretty much mastered by First Solar. Perovskite's coming up. Kesterites, people are trying them in the labs and trying to see where we'll find out where they end up with reliability-wise. That's the next big question. You get SIGs, other things. So if you start finding the right technologies in thin film, if you can start laminating them together, the first step is to do 2. So you can do perovskite over silicon, and the optimal place there to be is between 1.6 and 1.7 EV, a band gap, compared to silicon's 1.1. And now you could say, well, let me chop that up a little differently. I can do 0.9, I can do 1, I can do 1.4, I can do 1.7. Imagine that. Then you'd get more and more efficiency because you're basically taking that solar spectrum and getting the maximum voltage you can get out of each section of the solar spectrum.
Great.
Yeah, out of all those photons.
That's pretty cool. And so where can people get this technology?
Well, Caelux is on the forefront right now. We're sort of the leaders right now in making 1x2 meter panels. I think we're the only people in the Western Hemisphere right now making full-size panels out of perovskite. A lot of companies are working on smaller formats, and a lot of people are trying to just go after records for little tiny itty-bitty devices that are really no practical use. But it does get them on the NREL chart. I was just at the PACT conference in town saying, hey guys, let's create a reliability chart so that people, because that's really what's going to matter for making this stuff on large scale. And let's also start calling out, the size of those panels.
Yeah, when they make those little NREL record making solar cells, what are they, like a square centimeter or something like that?
Some of the record devices are 0.1 centimeters square.
0.1 square centimeter. So you make something that's 0.1 square centimeter, and how much does it cost to make a world record holder? It's like $1 million.
Well, there's the lab equipment alone, right? It depends on how you amortize that. How do you divide up that CapEx? But I have $1 million or more.
So $1 million for like a tenth of a square centimeter. How much per watt, I wonder, that costs? That's like some expensive.
It's worse than space cells.
It's like $1 billion per watt or something like that.
I mean, the researchers, right, in the labs like that, they're trying to push that boundary, or they're serving a very important function. I'd love it if the rest of the academic world would get focused on the reliability one. So that's why I think if we can get a chart out there that says, hey, let's make sure that those academics all have a badge of honor that they can use for their tenure committee to say, hey, I'm the world record holder for a perovskite that can handle light and heat for 10,000 hours, right? That would be great if we can keep everybody motivated and aligned on the right problem, right? So, John Doerr, metrics that matter, right? Measure what matters. I've forgotten the name of the book now, but that's the problem. So let's go focus on the right thing. For industry, that's what's really going to matter, and for really applying this stuff.
Instead of the $1 billion per watt, I always thought it was probably like a square centimeter and $1 million, and it's like, I was off by quite a few orders of magnitude, like 10,000 or something like that.
Space cells right now go for, I think, a few $100s a watt, or at least $100 a watt for sure.
I've heard now they're even sending some crystalline up there, like just regular crystalline silicon. I don't know, like maybe.
Yeah, but we sent perovskites in space, by the way. We sent our stuff in space, and it did quite well, actually.
Did you bring it yourself?
I wish. My dad was an astronaut trainee. He was the first trainee from the state of New York, actually.
Oh, yeah? Did he go up?
He did not. He developed asthma, and once you had any small physical ailment, you were done.
Yeah, I don't have asthma. Maybe I could get up there.
Get in shape. That's for sure, right?
Maybe do some push-ups.
Yeah. I don't know. At my age, I'm certainly those days are past any possibility for sure.
Well, that's pretty cool. So where can people, like, is this available right now, or is it?
We're not selling it yet. Sorry, I didn't quite finish answering your question. So no, we're aiming to release this year. And so we're going to first be working with partners, and we're going to get this into some fielded studies, and we're getting full-size panels, hopefully very shortly, out in the field to start, vetting how they perform and making sure that they do that.
And
but you need the field data.
And where are they making it?
We're making them right in Baldwin Park, California, just on the outskirts of Los Angeles, near Pasadena.
Gosh, I could probably almost ride a bike there. It'd be like a long bike ride.
From here, yeah.
Yeah, because we're in San Diego at InterSolar.
That's right.
So, yeah, that's pretty darn cool. They're making it in Southern California, and 2 square meters, pieces of glass, and any other applications?
Not right now. Right now, we're not looking at other markets. We're mainly focused on that terrestrial, big scale market. Well, we would start in the power plant world to begin with. That's where we're doing some of our initial studies of small pilot size facilities like 100 kilowatts. So we're going to be releasing one of those hopefully this year, very soon, hopefully. And then, we'll be learning from that. And then, we'll eventually be moving on to where the real value is in residential rooftops.
Yeah.
So a residential rooftop, if we add about 20% more power to the total output of this whole thing. And so, if a system costs you $3 a watt to put on your roof, and you say, okay, I can actually just increase the power by adding a tiny amount of cost, guess what? You just made, instead of $3 a watt, you suddenly cut that cost by 20%.
Sure.
So now you're at $240. Guess what? You would definitely buy that system all day long rather than the $3 system.
So what efficiency are we looking at for these modules after they're made?
We're aiming for a first release. We're aiming for 26.5%.
26.5%. That's pretty cool.
Yeah. And so the best modules you can see, I saw downstairs as walking around. No, I didn't see every single panel that was down there, but some of the best numbers I saw out of pure silicon were 23.2.
So are you signing all those companies up?
Yeah, we have agreements with a few of them, actually, some of the super majors,
Great.
So
you probably can't tell me yet who
No,
those,
not yet. But we're starting to work with them. And then we have one partner in particular that's been great with us, and we have meetings every 2 weeks, and we ship samples to them all the time.
Maybe what I'll do is I'll leave this microphone on you, and then I'll get to eavesdrop and figure out who it is.
Well, I hope I'll get in trouble with everybody, but okay.
Cool. That's awesome. Yep. So do you live down here?
I did. I moved down from the Bay Area to move down here to be part of this because I just felt like perovskites were the next obvious step. Moving to a tunable thin film, tunable band gap, thin film technology seemed like the next.
So do you know the history of perovskites? Like, who started developing it?
Yeah, so it started, the mineral itself, there's a mineral version of this that was discovered in Russia in the 1880s or something. The name perovskite comes from Perovsky, a Russian named Perovsky. It was actually, he didn't name it that, but there was a German later on, many years later, who said, well, call them perovskites because they were interesting.
Well, they didn't even know what to do with it.
They didn't know what to do with it back then. It was a totally different molecule. Actually, it had the same structure. So the structure was kind of like this rhomboidal structure that's inside of a cube. And so the first people who started developing it as a solar cell, there was a group in Japan. I think it was Fujiwara's group. But anyways, a group in Japan started this and took this to, so they started publishing papers saying, hey, we're getting, meaningful efficiencies out of this. A whole bunch of people have been contributing for years now. And slowly it's like one idea on top of another on top of another. If you look at the NREL chart, right, you've seen the perovskite curve going up at about 8 times the slope of silicon.
Oh, great.
Yeah, if you want to take a guess, when was the first 25% silicon cell made?
Oh, the first 25%? How about 2005? I don't know.
You're pretty close, yeah, around 2000. Yeah, I think 2000 was a 4 centimeter squared at UNSW.
Okay.
I think
That's
that was
the University of New South Wales, probably Martin Green.
Yeah.
Yep.
I think that was right. Maybe you might be right. It might have been 2005, but it was right around that period of time. So we're 25 years later, and we're still not making panels that are any better than that in large format, right?
Yeah.
So the learning curve is very, very slow for silicon.
Yeah, and then that one back then in the 2000s was probably some little small 1/10 of a centimeter square.
I think UNSW's was 4 square centimeters.
Oh, wow.
It was a Pearl cell. I think it was Pearl technology they called it. Yeah.
4 square centimeters. Ooh.
Yeah.
Good old 2x2, almost a whole square inch.
I think SunPower hit a 25%, 120 square centimeter cell in 2014. It was when I was there.
Okay.
I remember Dave Smith at SunPower, got the champion cell. They got the number from NREL. I was very pumped that day.
So how do you feel about, because you worked at SunPower and they just went under, I guess, pretty much. They still have the Maxion solar cells. I see Maxions here at the conference, and they have stickers all over the walls. But it was kind of sad to see SunPower sort of disappear there recently.
Yeah, I mean, it's funny, right? They split the brand into, hey, the sales and marketing, half of things, and installation and distribution is now branded SunPower. And then Maxion is still alive and doing well, you know, but they've got a majority ownership by other companies now. So it is a little bit too bad, right? It was an interesting technology, and it's almost like they were ahead of their time because it was a very efficient technology, but an expensive technology. And now that people are sort of realizing, hey, we need that little extra bit of efficiency, it might be worth it. Now there's other people coming into the IBC architecture. But it's important to pick the right architecture, which is why this 4T versus 2T thing for perovskites is kind of super important right now. It's like, well, 4T eliminates all these other problems. It actually gives you way more flexibility in the chemistry. It's not quite as efficient as a 2T theoretically, but gosh, it has all these other advantages. So it'll be interesting to see which one wins.
So when you were working for SunPower, were you working in the Bay Area there?
Yeah, I was up.
Did you know Mark Morose?
No.
He was the trainer, and I ended up getting like SunPower certified in 2008 and stuff like that.
Right.
But he was like in the solar industry since the real early days in like the 1970s, doing soldering together space cells. But super nice guy, great solar instructor. But he recently passed away. So.
Oh, I'm sorry to hear that. It's like Frederick Dross. Yeah.
Yeah, I did get, and it was kind of interesting because I did have him on the podcast. I didn't even know he was sick. And then I just heard not too long after, and I was like, wow.
Sorry to hear that. Yeah, the name sounded familiar. He was probably up at the Richmond site.
Yeah.
So my first year I was at the Richmond site, and then I moved down to San Jose site. Later, luckily I was living in Danville, so I could commute either way.
Yeah.
But yeah, I didn't know him, but spent a lot of time on that training roof, and it was good times early days.
Yeah, maybe you probably weren't there at the same time as he was. He went off to Sun Edison and different places.
Yeah, I was there I started in 2011 at SunPower.
So yeah, maybe he was gone by then.
Okay.
That's probably what happened. Yeah.
All right.
But yeah, it was really sad to see them go. And I noticed that, did you work with PowerLight and the PowerGuard product that they have?
Well, so I remember PowerGuard. I kind of tell you, it's a funny thing. It was like the luckiest thing for my career, actually, personally. And, you can work hard and be smart, do all kinds of good things. And sometimes there's just luck involved, right? And so one of the luckiest things for my career turned out to be that SunPower had acquired PowerLight. And the reason for that was I went to SunPower, I was heading up, but I was hired to manage a team that was the performance modeling team for modeling power plants and then trying to accurately predict the output within 1% on average for the year.
That's pretty good.
That was the goal, and we did pretty close to that.
That's better than any weather forecaster.
Yeah, well, I mean, you're averaging over a lot of weather. So the other interesting, and weather adjusted, by the way. So if the weather was worse that year, we still counted as a win. It's not our fault, the weather, right?
Yeah.
We didn't try to predict the weather, but we tried to predict the output relative to the weather. Then in the second year, they said, hey, would you be interested in taking on this other team, the reliability team? Sure, it sounds like a lot of reliability research and development. And so we were getting into a lot of the physics and science of how panels degrade. And it was a really exciting time in solar because none of the IC 61215 had been established, but it still needed a lot of work and needed people to recognize the limits and what new tests were needed, like 62804 for PID, for example. All those things still had to be learned. So it was an exciting time.
So those are all these IEC, International Electrotechnical Commission standards?
Correct, yes. Yeah, excellent. Thanks for translating the shorthand. So what was lucky for me was that because SunPower owned PowerLight's fleet, we could actually watch how, and PowerLight had installed Sanyo, they had installed maybe 10 different brands. And so, of course, NREL, then, and that back in those days was like, hey, we need to really understand what these degradation rates are like. And we were working with Black and Veatch and others to try to establish, hey, what are degradation rates really like for SunPower's fleet? And we could compare it to the other panels, and we could see that it was better. So we had a motivation to publish that. And then furthermore, NREL really had a big push, really had a big motivation to get us to publish that. So Sarah Kurtz was, I owe a lot of my career to her because she was, pulling me in and saying, Charlie, can you show us charts of Pareto's of failure modes? Can you show us and compare, different technologies? And we were one of the few people who had all the data to do it in a substantial amount of data.
Great.
So it was really great.
Cool.
Yeah.
Yeah, so recently somebody even told me that they had a whole bunch of PowerGuard. And so just to kind of explain what it is it's like tongue and groove, foam insulation, and then a couple inches above that is a PV laminate, which is a solar module without any aluminum frames or anything. And it's flat, and you put it on the roof, and it insulates the roof, and it's really cool. And so I designed a project. It was like a megawatt of that stuff a long time ago. And so this system, I think it's like, hundreds of kilowatts.
It's basically
like
a glue down on the roof type of thing.
600 to 800 kilowatts. Ballasted.
Ballasted, was it?
Just
Okay.
sitting down on the roof.
I remember the
just
foam. I remember the foam pieces that.
Yeah, and they just kind of like tongue and groove go together, and then
Right.
like there's these ballast trays around the outside, and they put the paving, the piece of concrete on there, holds it down, do the wind stuff and everything, and they put them on top of malls and stuff like that, and it's completely flat, so you don't have to worry about inter-row shading and all that kind of stuff. And
So you get the maximum power out of that roof that way. Yeah, for sure.
So their systems is almost 20 years old, and they need to fix the leaky roof, and they don't know what to do with it. And somebody wanted to charge them like $100,000 to recycle it.
Geez, really? That's a bummer.
Yeah, and I'm thinking like, well, there's got to be people out there. And so I did introduce him to a recycling company, and hopefully it gets reused. But one of the problems with this old SunPower stuff is it has to be positively grounded. So I don't remember the exact year where they fixed that, and it doesn't have to be positively grounded. So you need to have some kind of special inverter to make it work. So,
Yeah, no, that's a sticking point. And those are probably the ones from before around 2013, 2012, somewhere around there is when
that's about
we
when it
basically
happened.
got that
sounds right.
converted over. Yeah,
Mhm.
that's right. Yeah.
Yeah, but those were the good old fun, positively grounded days.
Yeah, I was part of the team that was qualifying the solution to that problem,
Yeah,
actually. I remember. Yeah, that was
yeah.
good. So you brought up an interesting problem of recyclability, right? So these panels are super durable, which is great from a performance and output perspective, and then such a bummer when you need to recycle it. It's like, oh, this is super hard to recycle. For perovskites, it's interesting. It turns out, I think we can take these, we haven't completely worked out that process yet, but I think there's a big opportunity to do this in a lot easier way. So I think we can take the glass, we can break the edge seals, and if we just break the edge seals, the material, once you allow moisture to get in there, the perovskite actually is quite sensitive to moisture. And so these two layers should be able to delaminate quite easily.
And then you can just dissolve it.
And then we can just dissolve it. And so actually the process of making a lead acid battery is the first thing you do is you take a bunch of lead that's left, recycle. When you take your battery to recycle it, currently the battery industry in the United States has achieved 90% recycling rates.
Yeah, it's like the poster child.
It is. That's what we want to do. So like, okay, how can we do that? Well, guess what? The chemistry is exactly the same. They take that lead, they take it all out of the battery, they dissolve it with a carboxylate in a high pH environment, and then they basically turn it into a solution to make a lead salt. And guess what we start with? Guess what perovskite turns into when you just expose it to water?
I guess the lead salt. Yep.
Yeah. So actually it could be really easy to recycle, we think.
Right.
So we haven't completely worked out the details of that process, but it could actually be a huge boost to the recyclability.
Pretty cool, yeah. And then as far as recycling the silicon, it's pretty inert and stuff like that. It's the second most abundant element in the Earth's crust.
You're right.
And so it's not that big of a deal, but it does take a lot of energy to remelt it and all that kind of stuff.
It does. And then furthermore, there's quite a bit of lead in silicon solar panels. And we actually have less lead in perovskite solar panels than there is in a traditional silicon solar panel. They don't use an unleaded solder. I remember SunPower was using a non-leaded solder, but most manufacturers aren't. So there's quite a bit of lead in there, actually.
Okay. All right. Cool. Well, don't want to be led astray.
Yeah.
Sorry.
Dad jokes.
Yeah, I got a kid, yes. So let's see, anything else we should cover? Or,
No, I think that's it. I mean, I guess I'll talk about more in my panel session tomorrow, but there's really a few things we still got to get right with perovskites.
What's the title of your panel session?
Oh, it's the future of solar. What are the future technologies and what do they look like? And then
like 200 years, probably.
Yeah, well, probably. I think they're looking more on the 10 to 20 year time frame. What's the next decade look
I've
like?
got like lots of bets on what's going to happen in 200 years.
Yeah. What's your bet?
That your product is going to be on every piece of glass and desk and even on our clothes, and it's going to be like turning light into electricity and turning electricity back into light. So how's that? Yeah.
Remember, you made a joke with Scott that you're going to have glasses with the perovskites on them, and you're going to be powering your powering your brain with that. Yeah. We'll see for sure.
Great. All right. Well, thanks, Charlie.
All right. Thank you.
All right.
Thanks for having me.
And how do people find you?
ch@caelux.com is fine.
All right.
Yeah.
All right.
CAELUX. That's CAE is heaven and LUX is light in Latin.
Oh, so CAE is heaven in Latin. Okay. Thanks for joining us here in CAE Luxland over here with Charlie Hasselbrink. And thanks for listening to Sean White's Solar and Energy Storage Podcast. To find out more, go to solarsean.com and take some classes. Get yourself NABCEP certified. And once again, this is recorded at InterSolar in San Diego.